So all these advanced techniques will combine on and include on our next unit test. Remember long division. Right, we've got our divisor, our quotient, plus our remainder, and you can take your division statement, divide everything by d, and that means any polynomial divided by something can be written as a quotient plus the remainder divided by d. And this is going to be important, and we're going to use this where it looks like substitution, but actually substitution does not work. So why do these look like substitution? Because you have a polynomial on the top, a polynomial on the bottom, and you're like, well, maybe if I took the derivative of the top, I would get the bottom, right? This one would be extra mean if I actually had, if I put the derivative right on the bottom, like the derivative of the top is 6x squared, or sorry, 9x squared minus 2x minus 5. I could put that on the bottom and you would be like, oh, it's substitution, and it absolutely is not. But it would sure look like it. You're like, thanks a lot. So if we have something like this, and you wanted to use substitution, the inside function would be the one on the bottom. It wouldn't be the one on the top. And if that one on the bottom is x minus 2, well, its derivative definitely doesn't match up with the top. So we have to remember our long division or synthetic division. So here's a review of synthetic division. Synthetic division says, write the coefficients of your top function that you're dividing, 3, -1, -5, and 1. Outside, write the opposite number, opposite sign of what you're dividing by. So we're dividing by x minus 2, so we put a plus 2 out in front. Bring down the 3, multiply, add. Multiply 2 times 5, 10, add. Multiply 2 times 5 again, 10, add. And you would get that, here's our division statement. That the original, and this is all f of x, that whole thing is equal to the quotient plus your remainder still would need to get divided by x minus 2. Why is this helpful? The original one we couldn't integrate using any of our techniques. But if we rewrote the original as 3x squared plus 5x plus 5, each of those are easy to integrate. And then you get the remainder, which is 11 over x minus 2, which is actually an easy logarithm integral. Because a 1 over x is natural log of x, right? And this is 1 over x minus 2. There's no crazy number there. That's going to be an easy logarithm. So we get the integral of this, and this will be x cubed, 5x squared over 2, 5x, and then this 11 will be 11 natural log of the absolute value of x minus 2 plus c. All right.
Fine.
Now we had synthetic division that we could use if you had x plus something, x minus something. But in grade 12, if you were dividing by a 3x minus 5, that's where we used our long division. Right? I undid that, and I immediately saw smiles like, oh, I can't wait to do this again. There was no groans whatsoever. Just for clarity on the video, we want to make sure that everybody's aware of the positive attitude we have in this classroom. Yes.
Why can't we just use synthetic division with, say, 5/3?
We could. So there are synthetic division techniques where you change your 3x minus 5 to x minus 5/3. But if you change this to x minus 5/3, you've actually done what? Factored out a 1/3. So you would have to deal with that 1/3 out in front of the equation as well. But the long division isn't crazy, so we could use it. But there is that option. I don't mind reviewing the long division here as well. So again, how do we do long division? For the blue, we're saying, what would I need to multiply the 3x by to get 6x to the 4? I'd have to multiply by 2x cubed. Then I multiply and distribute 2x cubed times 3x is 6x 4, 2x cubed times minus 5, minus 10x cubed, put it in brackets and subtract. Bring down the next number. Now in green, what would I have to multiply 3x by to get 3x cubed? I'd have to multiply by x squared. So I'll let you, it's color coded because you do the same process in blue, you redo it in green, and the same process again in purple, and the same process in red. And you get a remainder of 20, which means that this whole thing could be written as the quotient plus the remainder still needs to be divided by 3x minus 5. And then integrating each of those is going to be relatively straightforward with a natural log at the end. Right, that's what it would look. If you wanted to use the synthetic division, x minus 5/3, you'd have to factor in a 1/3. This 1/3 could come out in front as a 3 and deal with that at the end. Definitely try that. What's the issue with this with synthetic division? You've got a fraction for all of your math. So you'd be dealing with fraction work all the way through, but still doable. But the next two have x squareds in them, which means we have to use our long division or develop some very unique techniques for synthetic division that will take too long. So highly recommend using long division. Try those next two. All right, did you get the long division? The long division, set it up like this. First of all, to get an x cubed, you'd have to multiply by x. You could have put a 0x squared in here. But when I multiply by x and subtract, I get 6x plus 12. In fact, this whole thing is the remainder because now there's nothing, like you have an x squared out in front and you need to get an x, and the x is a lower degree than the x squared. That whole thing is our remainder. So here's our original equation. We can now write it as this. At first look, you're like, did that really help? And the answer is yes, because now I have our regular substitution. My inside function, the bottom, is x squared. What's the derivative of x squared? A 2x. So it's looking like I have a possibility of a substitution. However, I have an issue because what's the derivative of the bottom? 2x. And I have an x here, but I also have a plus 12. So I also have to use the algebraic manipulation strategy of unadding those fractions. Okay, so now the x I can do, this one is going to be substitution. And do you recognize what the last one is going to be? Is it,
Is it completing this?
is it completing the square? No. It sort of is, but it's already completed. Do you see that you have an x squared plus 1 on the bottom? That's a tan inverse.
12 times 10.
So, we've broken it up. This integral is the easiest. It's x squared over 2. The second integral, that would be a substitution one. And because we have a 6x, we'd have to multiply by 3. The second one works out to 3 natural log of the absolute value of u plus c, which is 3 natural log x squared plus 1. You see, I took away the absolute values because x squared plus 1 is always positive. If you left them there, it's not wrong. And then the third one is tan inverse. So this integral, all those different c's, is going to be x squared over 2 plus 3 natural log of the absolute value of x squared plus 1 plus 12 tan inverse of x plus c. That's kind of crazy. A whole bunch of techniques built into one. So we have to be good at all of our techniques so that you can see when to use them, when to break up things. The best way to get really good at them is practicing. So the more you do these, the more you start to see something. Okay? And one of the strategies that I sometimes use, okay, like in this case, you might have been really tempted at the beginning to make the u the top, the du the bottom. Or I mean, sort of like u substitution, because the derivative of 3x cubed is x squared. And you might like, this looks like a good u substitution. But u on the top is not the inside function. The inside function would be on the bottom. And this is why it's problematic in this situation. We use long division and we do not like what it looks like afterwards. But at least the x you can do the integral of. Then I saw that the bottom's derivative matched up with part of the top. So that's why I said, well, maybe if I broke up the top, then this part, now I got 2 parts that I can do. And I have to deal with the last thing, and the last thing ends up working out perfectly to be a tan inverse. For me personally, I would have gone from this to this in one step. I can integrate this one. I could do a little u substitution for this one. I'd still do that and write it out. But if separating each one separately too is not bad. All right, one to go. Again, it looks like maybe you should do substitution, but the inside function would be the bottom. So we have to use long division. Just to show of hands, how many people would like a more thorough explanation of long division? Or is what you see, are you remembering it? So there's a few. I will go through a more thorough explanation as we go through this one. So maybe don't write it down, just watch, see if it makes sense for you as you're watching. Okay? What you're doing to start off with, after you've written out what's in black, you look at this first term, which is x cubed, and you look at the first term that you have in whatever you're dividing by, which is x squared, and you say, what would I have to multiply x squared by to get x cubed? That's my green x. That green x then gets distributed to each one of those, giving me x cubed minus 2x squared plus 2x, which we've written in green, and then you subtract. After subtracting, you get a new first term, and you do the same process over and over again until your new first term isn't something you can multiply by, and that becomes the remainder. Oh yeah, I'll show you the answer to this one tomorrow. I'll put the answers up on the video so that it's available.